So, guten Morgen. Heute werden wir uns weiter mit der Systemsicherheit beschäftigen und zwar weiterhin mit der Functional Safety. Während wir beim letzten Mal eher uns darum gekümmert haben, wie man auch konkret Software und Hardware-Software-Systeme zuverlässig macht, geht es heute nochmal um Anforderungen funktionaler Sicherheit. Also es geht nicht so sehr um direkt die Techniken, um das zu realisieren, sondern eher, was sind Anforderungen und wie kann man bestimmte Strategien für sichere Systeme hier implementieren. I start in English or I repeat in English. Functional safety, there's a very good description on Wikipedia, and if you want to have more information, you can find this specifically and also information on very many standards like IEC standards and especially ISO standards there on Wikipedia. So normally when you would like to see such standards describing such reliability or safety measures, you would have to buy the standard from the appropriate organization, but the summaries you can find, especially on Wikipedia, are very good. Sometimes also some companies offer software in that field, and often on the home pages of these companies you can also find good summaries on the background of this. Okay, so you can have redundant information without purchasing these standards. Okay. The objective of functional safety is freedom from unacceptable risk, and such risk is physical injury or damage to the health of people, or it is also damage to property, and that can be both directly and indirectly. Functional safety standards focus on combination of electrical, electronic, and programmable systems. So, as we have seen in the previous session, such systems always consist of hardware in combination with software, and function is typically defined by software, so it has to be regarded altogether. And functional safety also has to treat the function of a component or a subsystem as a part of the function of the whole system. Okay, you cannot just look at a system like for instance, autonomous driving when you do not regard the complete traffic system. That is quite, I would say, that is quite straightforward. On the other hand, we have seen an example, for instance, for that radiation therapy machine. The software was just developed as the software without regarding the appropriate hardware, nor regarding the way in which the complete system was used and how procedures are of radiation therapy, and this just focus on a software aspect was the main reason that these severe accidents happened. So that means functional safety methods have to be extended to the non-EEPS parts of the system. So E is electrical, E is electronic, and P is programmable system. And also we have seen it must be verified considering the whole system in its environment in which it interacts and with which it interacts, and that also includes the operators, and that also means people who operate such a system or who are present in such a system, and their behavior must be taken into account. And these are aspects we are going to treat today. Here is, let's say, a statement that says functional safety is achieved when every specified safety function is carried out and the level of performance required of each safety function is met. Okay, here is something quite new. Here we have an introduction to safety functions. The strange thing is that in all of the information I was using, the term of safety function was never clearly defined in the beginning, but it was more, let's say, described in an implicit way. So I would say a safety function is something which becomes active when a system is having a fault or a failure. In that situation, a safety function must become active, and it must, for instance, bring the system into a safe state. Though that means failures can happen, but when the failure or fault has happened, a safety function must become active. So how do we get safety functions? The required safety functions must be identified. Hazards and safety functions have to be known. So a hazard is something, you could also say it's a danger. And a safety function have to be known. So how can we know these? For instance, we can resort to a FMEA to identify such functions. We have hazard analysis and hazard and operability studies. Also, what is important is accident reviews. So that's important to learn from previous things that went wrong. So there is typically a chain of action or a chain of the accident, and such chains must be analyzed. They typically have special patterns. Okay, then we have assessment of the risk reduction required by the safety function. So that means something goes wrong and we have to find out what will a safety function have to do. And also we have to quantify safety. And here a so-called safety integrity level is introduced. A safety integrity level is something like the complementary of a risk. So it gives us again a probability of a failure or some hazard, and the effect this has. We must, when we have such a safety function, we must make sure that the safety function performs to the design intent, even under incorrect operator input. That means typically such a safety function is an automated system. It is tolerant against user failures or user misactions. And that is also often straightforward. Imagine we have some safety function in a flying aircraft or in a driving car, so that system must frequently act very fast, and that means highest speeds can typically be achieved by automated systems. Okay. The design and life cycle must be managed by qualified engineers in accordance with recognized functional safety standards like IEC EN 61508 with derivatives or ISO 13849. So the IEC is the International Electrotechnical Commission. So these are all standards which are or this is a standard from the world of electrical engineering. Nevertheless, ISO also describes electrical electronic systems, here in ISO 13849. So the background is not so much which technology you use, but the background is more the application area. So IEC is more for generating and using such electronic systems. ISO is, for instance, also dealing with automotive technology, which is more mechanical engineering technology. Nevertheless, both use very similar standards and similar technologies here. When we do such functional safety activities, we must verify that the system meets the assigned system integrity level, or ASIL, which is automotive system integrity level, or and in that way several properties are important. One is the mean time between failures, because these in most cases are repairable systems, and we have a safe failure fraction, which I will explain in more detail. So these are properties, and of course for these we need to perform risk analysis, and implementing safety functions is already a technique of risk management then. The safe failure function is the probability of the system failing in a safe state. So we have probabilities of failure, and the system can fail in different ways. It can fail and it become a dangerous situation. It can come into a dangerous situation which we detect. It can come into a dangerous situation which we do not detect. It can fail and come into non-dangerous situations, so there are quite a number of probabilities. But when we detect such a situation which is dangerous and which we can bring into a safe state, then the probability that this will happen is the safe failure fraction. So it is important to note the mean time between failures, or the failure rate, describes the probability something evil will happen. Okay, we know this. The safe failure function is a measure when such a thing has happened, how probable is it that we can deal with it in a way the situation becomes safe. Yeah? let's say the following way, just a guess, an anti-brake locking system has, no, that's not a good example. Let's say a system where we have just steer-by-wire, yeah? And that system would have a mean time between failures of 100,000 hours. And what would that mean? 10,000 feet of failure rate. And now that probability is not so low because there are millions of cars driving around, so the probability is there such a system will fail. Of course, the probability can be calculated because we know all of the probabilities of failure of the individual components. And let's say we have 1,000 components in it, and every component has only a few feet of failure rate, then we will have a failure rate of 10,000 feet, and that means it would be state of the art. Such a system has a mean time to failures or mean time between failures of 100,000 hours. Okay, so that's state of the art. We cannot do much against it. So what we can do then is we can find a safe failure fraction. And that is something will come in which will bring that situation under control. In our case of steer-by-wire, I would say one of the most important things here would be something like redundancy. So we have a certain probability of failure that would be mainly determined by, for instance, parts count method. And on the other hand, when such a device fails, we have to avoid that the system can still be controlled. And that means such a system still has to be steered in some way. So what is the probability that redundancy will work? And of course, that probability must be very high, and that is then the safe failure fraction. In other cases, there could be another situation. For instance, we could say in the anti-brake locking system, so it normally when that fails, it could mean, okay, we do not need redundancy. If it fails, then it fails. It is normally sufficient when the driver is informed that he has no longer an anti-brake locking system. Of course, if he is just on ice and the system is failing, then the situation is not so good, but the probability that just such a thing will happen is very, very low. And in that way, again, the safe failure fraction would be high. So that means probability of failure and probability to deal with a failure are important properties which we need. Now let's deal a little this standard 61508 standard on functional safety of electronic programmable systems or related systems is an international standard published by the International Electrochemical Commission. When you have the PDF of these lecture notes, you can directly go to an appropriate link. And that standard is intended to be a basic functional safety standard applicable to all kinds of industry. In fact, many standards which are specific of certain industries have been derived from this. There are certain standards for, let's say, medical devices. There are certain standards made for aircraft industry, or let's say when we have ESA or NASA, they have standards derived specifically. So the standard covers the complete safety life cycle, and it can be adopted to such industrial sectors. In such a safety life cycle, we have 16 phases which are concerned with safety function. The first 5 phases, we will not go into these in detail, address analysis. Here it is important for you to know that we have all of these techniques of risk analysis we have already seen, like parts count method, like Markov analysis, like FMEA, and so on. And these analysis techniques are used in order to find out what can go wrong, and also how the system is structured, how dependencies are, and so on. Phases 6 to 13 address realization, yes, how to accomplish safety functions, and phases 14 and 16 address operation of that system. Okay. So standard typically, and that's the reason why I show it to you, has a number of parts, and normally every standard, also 61508, has general requirements. So that's more the environment where that standard has to be used and what the main goals are. And then specifically requirements for electrical, electronic, and programmable electronic safety-related systems. Then specifically something on software requirements. And so that's mainly what the standard requires. From number 4 on, we have definitions and abbreviations. So what is safety and so on. Then what is important in modern standards is often to give examples. So here we have examples of methods for the determination of safety integrity levels. Often these examples take more space than the first definition parts, or not the definition, but the requirements parts. And then there are also some guidelines, general how to apply it, especially number 2 and 3, which is the function and the software. And in number 7, again, we have an overview of techniques and measures. Okay, that is structure of such a typical standard. Maybe just a short remark how such a standard is derived. Normally we have these organizations. In these organizations, experts work either on a voluntary basis, or they are sent there to their companies, from their companies. So some big companies like, let's say, Siemens or Infineon, or maybe also the automotive suppliers, they say, okay, we cannot leave standards just to non-experts, but we want to have, first of all, our experts in it, and also we want to avoid that with such standards, let's say, requirements are defined which are either not helpful or which are detrimental to our business. Yeah, so it's a kind of policy which a big company needs, like similar like patent policy. So it is something how the rules are defined also by the players themselves. That's important, and I think if it's done in a reasonable way, it is okay. On the other hand, for instance, let's say if you have some experts from some automotive company and they do not write into a standard, for instance, that or if they allow that if you have a car on the test stand, it can use other software than when it's in normal operation, then it would be some kind of policy in order to bring the company a certain advantage. So I think making such standards must not only be accompanied by such big companies, but also by independent experts who have an eye on, let's say, on general requirements of this society. Okay, there are some views in that standard. Zero risk can never be reached, but that is something which is quite straightforward. Zero risk, in fact, it can only achieved when you avoid something completely. So you have zero risk from traffic, from automotive traffic, if you have no cars. Yeah, but that's not the way we want to go, because we want, of course, to implement technical systems. Safety must be considered from the beginning, so from the first idea of such a system, not build it and afterwards screw some safety devices to it, but it must be an integral part of the complete design and also of the specification. And non-tolerable risks must be reduced. And the first thing I already mentioned is we have to perform a hazard and risk analysis. So that means we must define what is the probability of all events that can happen, and for second, what are the consequences of these events. Okay, again, and all hazardous events must be treated. And these hazard and risk analysis techniques must both be qualitative and quantitative. Quantitative means we determine, for instance, a failure rate or a mean time to failure, or some Weibull curve, for instance, could be something which is important. And on the other hand, a more qualitative method is something like the FMEA. Now, let's first have a look at the probability that some failure occurs. And we have here categories: frequent, probable, occasional, remote, improbable, and incredible. So, when we have a system which operates continuously, we could say if it is many times in a system lifetime, it is frequent. If it's only several times, it is probable. And that means for instance, we have a failure per year. If it's above 1 promille, then it is frequent. 1 promille per year, that means for one individual system, it already means over a typical lifetime of 10 years, 1%. But now imagine we have 50 systems in operation, so we have almost 50% chance that something will fail in that way. Probable is 10 times less frequent, occasional again so, and if the probability is less than 10 to the power of -7 per year, then it's incredibly low. On the other hand, you could say we have how many cars worldwide? Several hundred millions. So again, that of course will mean that it is quite sure at least some such hazards will occur. So okay, these are the likelihood categories. Then we have the consequence categories. We have catastrophic, that means many people are killed, or at least several people are killed. Critical is if it's one killed, so marginal means we can have major injuries to one or more persons, and negligible is minor injuries at worst. What is important here in these definitions, we do not see loss to property, but only how people are affected as persons. And these 7 categories of likelihood and the 4 categories of consequence are combined into a risk class matrix. Okay, here we have 4 classes. So when we build up this matrix, of course, the worst thing is catastrophic and frequent. Okay, if every year a nuclear power station would blow up, of course, that would be something like, and that is the most less desired situation. So it's unacceptable in any circumstance. But again, frequent frequent appearance of hazards is also always unacceptable, even if it's only a marginal effect on persons. If it's so, you can see the both combination of frequent and severe consequence must be low, and again, the more to the upper left it is, the higher the risk is induced. If it's negligible and also incredible, of course, it's the best. It's acceptable as it stands, but there are also situations where we could say we must do a little more. For instance, here, if it's negligible and on the other hand remote, so it sometimes happens, then we could say maybe we have to address it, or if it's catastrophic and even if it's incredible, we have to watch the complete situation. So there should be some monitoring of that risk. For instance, in the implementation and in the operation phase. Class 3 is tolerable if the costs of risk reduction would exceed the improvement. So the cost of risk reduction, it's not so much here the costs as money, but it is also you can introduce other risks, also endangerment of people, and if such a thing would be brought in by safety functions, for instance, then of course it would make no sense. Then you have two possibilities: either don't realize such a system, or you realize it and you say, okay, it must be accepted, but the only alternative is omitted. Okay, in that way we have the four risk classes which are defined, in automotive, and these are the so-called SIL classes. That is safety integrity level, and so we have 1, 2, 3, 4 such risk classes, and in the classification of automotive there is some more aspect, which is the question of controllability. So if such a hazard occurs, the question is still, can a driver deal with that situation? For instance, as I mentioned, we have the anti-brake locking system. If you are in normal operation and that system fails, the driver can deal with it. So he can drive slower, he can shut down the motor and go walking or something like that. On the other hand, if his steer-by-wire system fails, probably the situation is hardly controllable. Yeah? And in that way, they can define controllability: generally controllable, simply controllable, normally controllable, so that is most drivers, or difficult to control or uncontrollable. Here we must also say that when it goes about controllability, there is a very strong effect of training. Yeah, training is normally nothing done in driving. You get your license and then you get more and more experience. Maybe by coming into some situations just by chance, you can maybe deal with that situation, or for instance you drive on a slippy road but under controlled conditions, so you can train a little how to drive on an icy road, and then in a critical situation you can deal with it in a better way. So that would be maybe some self-training. Until some time ago I was a private pilot, and so in sailing and glider flying, training is very important also for pilots which have a license, and so every year you do some check flight and you make some certain exercises which simulate critical situations, and that is very helpful to bring you into a state where you can better control. In automotive, when people set up such a thing, normally the engineers must start from the situation that the normal driver is dumb and untrained. So now when we have these classes, how critical it is. So we have the SIL classes, and for these classes we must specify which probabilities of dangerous failures we allow. And there are mainly two aspects how we can treat such a system. One is the low demand mode. That means we only have a system which is operated from time to time. So sometimes it is turned on or such a thing. The question is, when it is used, then will there be a probability of failure or not? So that's an absolute probability. And the question how probable it is that it will fail when you use it a single time. So that can be between 1% and 10%. That would be the SIL class 1. So that is quite probable. Yeah. We have the SIL class 2. That would mean between 1% and 1 promille. And the SIL class 3 would mean 1 promille to 100 ppm, parts per million, or 10 promille. And the next would be better than between 10 to the power of -5 and 10 to the power of -4 as a probability that it will not work. So that could be, for instance, an anti-brake locking system. How often will you use it? Maybe not so often in the lifetime of your car. Maybe 1,000 times or so in the lifetime of a car. Not even every day you will need the anti-brake locking system. But on the other hand, you want to have a high probability that it will work when you need it. On the other hand, you have many systems which are used continuously. So computer systems acting all of the time. You have a chemical plant where some control computer has to control it all day, all night, over years. And then, of course, in that high demand mode or continuous mode, it is relevant to know about the probabilities per time. And here, even a probability of 10 to the power of -6 to 10 to the power of -5 would be SIL class 1. That means that probability is 1,000 fit to 10,000 fit, and a higher probability or of higher failure rate we cannot accept for SIL class 1. So in that way we can say we define SIL classes by the probabilities which we have and by the hazard which can occur, and for these SIL classes later on we define probabilities of dangerous failures which are accepted in these classes. Of course, these probabilities could be decreased in the future. So if you say state of the art could make systems more and more safe, then of course in the standards these values could be lowered. You could say, okay, then maybe not 1%, but only a 10% is acceptable. But in that way we have defined safety integrity levels. And of course, a safety integrity level is something which is a design target in our system which we design. But now let's go specifically back to safety functions. So we have defined safety integrity levels. On the other hand, we have seen failures can happen, and if the failure can happen, the consequence can be has to be expected. But functional safety in automotive is generally to prevent dangerous failures in automotive control units. On the other hand, nothing can be failure-free, but the consequences can be avoided. And there are three main targets when we have automotive control or automotive functions. The one thing is avoid systematic faults and failures during design, development, and manufacturing. So better here to write also failures. Even experts sometimes use such terms a little sloppy. And so we can make systematic faults during design, development, and manufacturing. So that could be some kind of misdesign, or some behavior has not been implemented, or you could say maybe you have just not a good thermal design, so it will overheat and such a thing. We must avoid such systematic faults during design, development, and manufacturing. Then we can also have systematic faults during operation. Such faults or failures can be again something from external effects. It can again be something which comes from the environment, or I would say if it has to do with electromagnetic control or such thing. Okay, such faults could happen during operation. And we can also have random hardware failures during operation. So it's just, let's say, failing by chance. We have the normal exponential distribution. Some devices fail from time to time. And in that way, it is important, especially to see for systematic faults here. Now, give us an example. That's a car. The car has some steering wheel. The car has also a traction unit, and so there are quite a number of elements which can already fail, and again we can have many possibilities of failure. And imagine something like what would be a dangerous situation. Of course, extremely dangerous is when we cannot steer anymore during the driving. What can be somehow dangerous, but possibly not as dangerous as with steering, is when traction is lost. Maybe we are on the left lane on the Autobahn, and suddenly the motor goes out or a wheel is blocked. Then I would say that's already dangerous, but maybe not yet as dangerous as when you cannot steer anymore. But so that such a thing could happen. For instance, we could have a hardware failure, and of course the system will be in a safe state when there is no failure. But imagine something fails, yeah? Then we can have two possibilities. The either is it fails in a safe way. For instance, a component fails in our control unit, but a second control unit will take over and help us keeping the car steerable. Then it would be a fail-safe situation. It could be that this safety function which is implemented doesn't work. Then the whole system would fail dangerous, or what can also be, there is no safety function. There is no redundancy, or is no control switch which brings our car into a safe state. And of course, both are dangerous situations. So we have, in order to find out how we can deal with these cases, of course, we have several techniques. One is make it as reliable as possible. Yeah. So more reliable systems are typically also more safe. Yeah, because the probability of just hardware failures, random hardware failures, is reduced. If it fails, then the situation depends on whether we are able to bring it into a fail-safe situation. And for that, we first of all, we have to detect that failure, and we also have to deal with that failure using the safety function. And now imagine we would drive, and normally when we have our operation, we have a certain time until the fault is detected. Let's say, what would be a typical fault detection time, depending on whether it's what the typical control cycles in such a system are. I would say it is probably something in the 1 second range. So generally, it has to be detected if there is a fault. And after that, there is a fault reaction time. Just to give you an example, it could be the time until the second redundant system comes into action. So especially if it's a warm redundancy, it will take a time which is at least longer than the fault detection time. If it's a cold redundant system, then I would say normally it would not be suited to keep up safety. Okay, and then the system will stay in the safe state. On the other hand, that's a situation when the safety function has worked properly, but what has to be avoided is violation of the safety goal. That means the fault is not detected, or there is no proper reaction to that fault. Finally, okay, after we are in the safe state, the complete time is the so-called fault-tolerant time interval. What does it mean? That time must be short enough. That means that is the time the engineer has in order to bring the system into the safe state. You can estimate such time. For instance, you have a car driving at, what is it? Let's say 100 kilometers per hour. What is the speed? Then it is 30 meters per second. Yeah. So normally, you could say if you have a driver, how far can you look? Maybe you can have a overview of the next 100 meters. That means the failure somehow has the driver somehow has a fault-tolerant time of 3 seconds. So in 100 meters distance, there is something blocking, for instance, our driving. And now if we, from the instance on we see it, until that in 100 meter, we have this fault-tolerant time interval where the complete reaction must have been finished, because otherwise we would rush into that block of our road, for instance. So that means within the fault-tolerant time interval, the system must be in the safe state. And again, that time is of course something which has to be derived from a thorough analysis, because that is the time we have. And now the system must be designed in a way that it takes less time, and even taking into account uncertainties, the time must never be higher than the fault-tolerant time interval which is given us. Okay, and in that way, we can say now we have a completely new concept. We not only have a risk which can appear, but we have dangerous states, and we have to avoid after a failure, and we have to avoid dangerous states with a high probability and within a certain time, which is a fault-tolerant time interval. And in that way, we have already important safety goals, and of course these safety goals must be accomplished by our design actions. Again, to show it to you, normally we have a single point fault. So let's say something is breaking. Nothing will happen because by our system we do not have a safety mechanism. We have a safety goal impact that could be a real impact of the car somewhere, or impact of pedestrian or something like that. On the other hand, what a modern system must accomplish, we have a single point fault, so there's already a certain risk. We have a safety mechanism. We have detected that single point fault and we deal with it. So detection doesn't just mean we know it's there, but also we treat it. Or we have residual faults, and these residual faults are either faults which are not detected or which cannot be dealt with. Now we have the so-called safe failure fraction. So after we have a defect or have a failure, the safe failure fraction gives us the probability that the system can still come into the safe state. And it compares the high likelihood of dangerous failures with that of safe failures plus dangerous failures. So with the probability of all failures. So that's here, of course, 1 minus safe failure fraction. Reliability by itself is not sufficient to claim a SIL level. So in a SIL level, you cannot just say the probability it happens per event or per time gives me the SIL level, but we also must guarantee a certain safe failure fraction. When we have a no redundancy system, and we have a safe failure fraction of 60 to 90%. So that means with 60 to 90%, we can bring the system into the safe state. That can only give us SIL level 1. If the safe failure fraction is below 60%, so it can be made safe or not. That's roughly 50%, let's say it that way. Such a system is not allowed. If it's 90 to 99%, we can have SIL level 2. And if we have over 99% and we have a non-redundant system, we have SIL level 3, and only when we have single redundancy or double redundancy and a safe failure fraction of 99%, then we can get the highest SIL level of number 4. And that means these are targets which have to be achieved. So in the standard, we say we have probabilities of the individual failure categories, and we have as a second safe failure fractions, and in that way from our SIL level which we want to achieve, we have to derive safe failure fractions, and we have to derive probabilities or rates that are accepted as maximum. Okay, such a management summary that is given by Mr. Vitiello. He is the chief engineer in the Continental company, one of the biggest automotive suppliers. And so we have ASIL goals, and we have also we have these goals, and in order to make our system, we have first to perform hazard and risk analysis. Then we must build up a functional safety concept on the vehicle level. So that is typically done in cooperation with the car manufacturer, or OEM as we call them. And then the hardware-software safety mechanism is implemented, and that's on the control unit level. So last time we have seen how to develop control units, and when we have such a subsystem, again we must go into the analysis. Again, here we are on the vehicle level. Here we are on the control unit level, or on the subsystem level. We make an FMEA or other similar analysis. We have a fault tree analysis. We have a dependent failure analysis. We can have Markov processes and so on. That's all of the analysis we have already seen. And in that way, our system is improved. We have already seen FMEA is not just analysis. It always is a cyclic action of improvement analysis until we have reached the safety goals. And here it's in a similar way. And after that, we are finished. We go into the further development and production processes. There are also always certain safety assessments on subsequent levels. That is something which is very important in automotive industry. They not only have it for safety, but also generally for quality, so they call it quality gates. And in that way, during that action, we always have these different safety assessments. For instance, when we go into production, there can be additional risks, and in order to deal with these, the assessments in the different stages have to be performed. And in that way, hopefully we get a safe product. Now, just to show you several standards which are safety relevant. In automotive electronics, the most important standard for safe software is 26262. That is something which helps us make software and software controlled systems safe, but on the other hand, it also shows us that software according to ISO 26262, you could say for instance, the control part itself. So, for instance, you have a control loop you implement. It is the smallest part of the software. Most of the software then is for something like watching and keeping it safe and so on, and maybe having a backup when something goes wrong here, when we have a fault. So that means it is an important measure, but on the other hand, it makes software also much bigger. Then we have something different for railway software. The railroad people, for quite a long time, they were not so active in reliability techniques, because they said, okay, we started early and we are on a high level, and a track-guided system is inherently safe and so on, and so, but since they use software, also there's a specific standard. Then there is one of process industries, like chemical industry, which is very important. There's a certain standard, see the number is very similar to process industries, which is for nuclear power plants. And then there is one generally for machinery. Okay, you do not have to keep the numbers in mind. It's just to show you that this initial standard 61508 has been adapted to many fields of application. Okay. That means that's a modern concept how to make systems safe. So that goes beyond the initial idea that risk is the product of failure probability and severity, and if it's lower than some boundary value, we are on a safe side. But on the other hand, in modern systems, we go far beyond this. We have the so-called SIL levels, and these SIL levels, of course, they deal with the situation that very severe events can happen, but then the probability must be safe. And on the other hand, it also requires that we have safety functions, and these safety functions must work with a high probability and within a short reaction time. Okay. Now, maybe for the last part of today, there are some aspects of safety which are human factors. First of all, let's deal with labor safety, and let us the following. Until the 19th century, the situation was quite bad in the factories. So there were plenty of workers because the population was growing with a few percent per year, and so more and more population, young population came up. And on the other side, there were much industries, and in that way, the emerging population could work in the industries, but the growth of population was more than the growth of industry, and so there was an oversupply of people for work, and that would make them cheap, and this would make them dependent. Okay, so workers are disposable and available also maybe in many applications. At that time, a worker maybe didn't have to be so skilled, and because that was just the trick, going from craftsman economy to labor-based economy, that the skill had to be significantly lower by automation with simple machinery. And the idea was, okay, the worker accepts the risk of his job, and if he is subjected to risk and something happens, it's bad luck for him, or it's maybe his own fault, but it has nothing to do with the employer. Okay, therefore, let's say there was no compensation, and especially in America, the rules of legislation were, if someone was working to earn a living, if it was another worker's fault, and when the worker knew the risk, then there was no compensation, and explicitly not by the employer. Okay. And only from the year 1910 on, there was legislation, and there was also some court decisions which held the employers more liable, and especially it was addressing labor's health, so you wouldn't have to deal with such dangerous substances that your health would deteriorate, and also improve safety. So the employer was made more liable. On the other hand, it was until, let's say, World War II that the conditions were not so good for the laborers. I heard, for instance, of several examples. For instance, in the 1930s and 40s, beryllium was introduced as a special metal, for one in metallurgy and for second in special applications. Beryllium is a very strong material which is extremely light, but it is unfortunately the most poisonous material. Also, when you heat it, for instance, for welding, it will evaporate and these vapors are deadly. So in that case, workers were just dying, or they were getting some very severe lung disease. Okay, so that was the situation until shortly before 1950. On the other hand, in Germany, Mr. Heinrich, he was the first to systematically investigate industrial accidents. Mr. Heinrich, he found out that when you have when you look at accidents, you have the following relation. For instance, imagine you have something like 360 accidents. From these accidents, typically in industry, one is severe or was severe 100 years ago. 29 or 30 were minor injuries, and over 300 were accidents, but they didn't result in injuries. And that's so-called Heinrich's pyramid. It says, of course, that for one thing is, if you have an accident, most accidents are injury-free, but on the other hand, you have something like a probability of 3 promille that something severe will happen. And that means when you have 10 million employees, so you have 3 times 10 to the power of minus 3 times 10 to the power of 7, then that means you have at least 10,000 severe injuries. And this so-called Heinrich's pyramid, it just shows that that was at the first time when systematically accidents were regarded. Now it's a very important part. In Germany, there are, for instance, the Berufsgenossenschaft. It's some kind of employer's insurance. That Berufsgenossenschaft is kept up by contributions from also employers, and these have to pay for, let's say, for hospital, for treatment and so of injured people or of people who have job-related health problems. And especially the Berufsgenossenschaften, they give lots of instructions what to do and what to omit in order to avoid accidents and in order to avoid bad health. Okay, so the situation mainly, for one, it improved because there was better legislation. Also, that legislation included creating the Berufsgenossenschaften, but in Germany. But on the other hand, just giving power to the people who have to pay for it helped improve the situation. So now let's have a look at accidents. That's not only labor accidents, but generally accidents. And one thing is you could have, let's say, technical reasons. Yeah? You have systematic faults in the design, you have systematic faults in the operation, you have random failures of hardware, and if these come together, also if, let's say, the people involved are not able to control the situation, then we have an accident. That's more the chain of action as we tried to deal it with safety functions and risk analysis and so on. On the other hand, you could have another view which is more at the whole, let's say, how a system is, it's hard to say, what the safety culture is. So, just independent of these other aspects, you could say you have a safety culture where everybody and on every level is aiming at safety. It's similar with quality. Safety must be a goal by the highest management. Yeah? And if it's a goal and if it is enforced in the company, then also on the lower levels we have a safety culture. On the other hand, if the management doesn't have a safety and quality culture, of course the whole company will not be able to develop it. So there is some saying in German like wie der Herr, so's Geschirr, so like the farmer, so his tools will be, yes, so if he doesn't care about anything, his equipment will look like he is careless, so that is meant. And so one of the things of lack of safety culture is excessive confidence and indifference. That means, okay, nothing will happen, we are quite confident, and also when something happens elsewhere, it doesn't apply to us, it's another situation and something, yeah, you can also hear these arguments, for instance, in the connection of nuclear power stations. Of course, when you have a nuclear power station on the Rhine River, you cannot have a tsunami, so such things don't apply to us. So then is traveling down the risks. So if someone, for instance, brings up a risk, so you argue so long until he, yeah, okay, he gives in, and you say, okay, it's not as bad as it looks. And there's also a saying in German, nothing is eaten as hot as it is cooked. And in that way, risks can be trifled down. And such a trifling down is typical of lack of safety culture. Another thing which is more technical, and that's something you could be asked in the exam, is overrating of redundancy. So situations when redundancy will not work. Okay, for instance, warm redundancy you have, but you need hot redundancy. That would be one case. Another thing which is really important, and you deal with it, is common cause failures and common mode failures. Then we have unrealistic risk assessment. For some things you need really a thorough analysis, but something is just guessed. also something, sometimes a system is not able to detect a failure. For instance, there was an example in a chemical plant, and that chemical plant would blow up when the pressure would be too high. Then you have just an explosion. Okay, and there was a safety valve, and that safety valve, if it's open, the pressure can be released. And to be safe, how do you know the safety valve is open? You could do it the following way. You make a switch for the safety valve, and when the switch is in on position, at the same time a red lamp or a green lamp is lighted. Okay, you know the switch is in the safe position. On the other hand, what happened was the switch was in the safe reaction, but the valve blocked. So operator said the safety valve is open, but the valve was not open. So the situation was not assessed in a proper way. What it would have needed was a sensor which would show the valve is open, and then the sensor would feed back to a green lamp and say the valve is open. So in fact you would need two lamps. One is for the switch and the second is the feedback. Yes, the valve has done what it should do. It was a similar situation with that radiation therapy machinery. Another thing is neglecting events with a low probability but a large effect. So if you have something which has a very low probability, sometimes you neglect events. For instance, when you have a Markov chain, you have transitions. Yes, you have a number of states, and the number of transitions is just the number of states square. Yeah, so it increases progressively, and that's the reason why you try to omit as many as possible unprobable transitions. And the transition is, for instance, a failure. Yeah, and so if you have such events with low probability, you just omit them to make your analyzed system more simple. That means you can do it, but when such a low probability event has a large effect, you are not allowed to neglect it. You can assume a so-called learning curve. That is a reduction of risk over time. That is a general aspect. If you have any performance property over time, in the production or operation of a system, and here is time. So typically all things go down in some way. So that could be, for instance, costs or failures per produced parts. Defects per million, or just, let's say, defects or costs, or all of that will go down over time, and that is a so-called learning curve. Typically, for instance, when you want to be better than your competitor, for instance, your competitor has less failure rate of cars in the warranty time, yeah? And you improve yourself. You say, okay, I want, Volkswagen wants to be better than, let's say, Lada, yeah? Okay. And on the other hand, no, Lada wants to be better than Volkswagen. They improve, but they also must take into account that Volkswagen also will improve in the time they improve themselves. So that's a so-called learning curve strategy, which is very important, because that means normally with all things which you repeat continuously, you will become better. Of course, that doesn't mean you have no wear out or so. That is something different. But if you produce something always again, you just do it new from the beginning, then you will always improve because you get lots of routine things. The more parts you produce, the more often you do it, the more efficient you will be, and in that way you will have a continuous improvement. But you cannot just assume, okay, maybe according to today's state of the art, the system is not yet good enough, but then in a few years when we produce it, state of the art will be better, and also our system will be better by 50% or so. That is nothing you can or you should do. Software errors can be underrated, and these are quite complex because they are not just random failures, but there can be also something like systematic design faults in the software. And another thing is, as we have seen on top, ignoring early warning signals, similar events or even same events. Then people should pay attention. And on the other hand, you could say two things come together. One is the actions you really do, as we have seen them, which are the reliability engineering actions, but on the other hand, if there is no safety and reliability culture, all of these measures we take will not be efficient as they could be, because, for instance, in case of doubt, people would rather go the easier way and maybe not pay attention to what they have detected, or think it is too expensive or something like that. And that means in the end, if you do such technical actions, which you must do anyway, it's then always the question, will you go the easier and cheaper way, or will you go the way where it is more reliable and where it's more safe? Just for finishing, to give you an example, some decades ago, an American aircraft company, they had the question of their cabling, and the cabling has an insulation, and that insulation can be a normal plastic, which can burn, or it is an inflammable or more highly inflammable. And these, in the company, they were doing a calculation. They said, okay, if we have so many aircraft and so many kilometers of cabling, it will cost us so and so many millions more. On the other hand, if it's less safe and there are accidents, we think that such accidents will cost us so and so many $1 million. But these costs are lower than the costs for the better cabling, and so we take the inferior cabling. That was one of the reasons why in America later on so high compensation sums were decided by the courts, because just such behavior was to be avoided. For me, clearly that is not a safety culture, that's a very cold costs culture. And on the other hand, of course, both have to be balanced, but it also shows us that just taking technical actions without a good safety culture will not lead us to the target, and it will lead to risks which are avoidable. Okay, for today, thanks for your attention and see you next week.